for the introduction. Good afternoon, everyone. It's a pleasure to talk here in front of a full room still at this time before dinner. I will indeed talk about modeling, but on the device level rather than on the molecular level. First, to introduce our two organizations in Winterthur. So where is Winterthur? It's right here in, not far from Germany, not far from Zurich. This second biggest city outside of Zurich. And this is where this university is. I joined a while ago, and then in 2006, we spin out a company called Fluxim, and which is now still in Winterthur. And both groups have about a dozen staff members. We have one PhD student is here. Marcus is here. He will show a poster this week from Zeta AW. And then, yeah, of course, we are also happy to participate in several European projects, even though we are from Switzerland, which is yeah, one project is called Mostophos, which is currently running on OLED modeling. And so why modeling? Why should we care about modeling? Our motivation is, well, there are still some challenges with OLEDs. They are very efficient, but they are still, well, highly efficient, but there are some issues still, like efficiency roll-off. If you drive high current through the OLED, the efficiency can drop at high current density. Moreover, there are still some issues with lifetime stability over long operation periods. And we think that in order to find out what's going on, it's worth to do modeling. And modeling with sound physical models, so only put physical ingredients that we believe in, and then also try to make measurements that are comprehensive, try to combine many different techniques, steady state, transient, and so on. So this is a kind of a chart on different scales. On the left, so the first presentation today, or my first presentation, sorry, there will be more. My first talk will focus on electrical modeling on this scale of everything that happens in 100 nanometers between anode and cathode. So we use the drift diffusion modeling approach. And the previous presentations today dealt with density functional theory and so on. Then tomorrow I will talk about optical modeling. You see on the right-hand side. So we go also there in optics. We can cover different scales, thin film optics as well as ray optics. And then my last talk tomorrow will be on electrothermal modeling, because OLEDs, you want to make lighting panels, so there is some resistive losses. So that's in the centimeter scale, and that's the last part of my contribution to this summer school. Now, during these presentations, you will see some product placement in the sense that, well, I can't avoid mentioning them because we're trying to help the community by providing R&D tools. So the first one that I focus on in this lecture is on electrical modeling. ZETFOS is this simulation software that is more than 10 years old already. And then PIOS is a measurement instrument that is about 3 years old for electrical and optical measurements. And the third tool is the large area modeling tool that got born last year. So that's the newest tool. Now the main motivation for us, we don't want to just make simulation, but we also want to compare with real measurements. And in order to facilitate that, we achieved a kind of an interface between the measurement tool PIOS, which gives you this example, a pulsed OLED example. The line is the measurement, and after you finish measuring, you can already press a button to start simulation and try to reproduce what you just measured. So any kind of signal that you can measure, we want also to allow to do a simulation and make a direct comparison here in the same plot. So that's the challenge. Compare in the same plot. So this is the the list of talks tonight, electronic and excitonic modeling. And then after dinner, I didn't bring the instrument. It's a heavy suitcase, and I'm sorry for not bringing it this time. But nevertheless, I will give you an overview on different experimental characterization techniques, try to show which method is for what reason. And then, tomorrow is optics and large area modeling. So in this talk, you might be interested in excitons for sure, but before we go to that part, the second part, I have to introduce the drift diffusion modeling and charge transport, trapping and recombination, and then we go on with exciton modeling. And throughout, I will show some examples of simulations and a few measurements. That's the talk after dinner tonight. We'll go through characterization techniques in AC, DC, and transient. And I brought the picture, but not the instrument. Sorry for that. Now, first of all, device physics. The way we think of OLEDs is a device with thin films, and it's interesting to look at the cross section. We have anode injection from the left. We have cathode. We have hole injection and electron injection. And the state-of-the-art OLED has multiple layers, not just an emission layer. And there is particular reason for barriers of energy. You want to avoid that the electrons that is injected from the cathode through the electron transport layers, through the emission layer, it should not escape on the anode side. Otherwise, you have an inefficient OLED. The same applies for the holes. They should arrive in the emission layer, but they shouldn't go across this barrier and escape through the cathode. So there are some basic design rules for building up an OLED stack that is kind of visible here. And the third process here, the formation of an exciton here, an electron-hole pair, that's the interesting step. And of course, we have host-guest system, TADF, and so on. So that's where the excitonics is happening in the EML. And finally, we can also solve the light-out coupling problem by simulation. There is thin-film interference and so on. Now, let's look at the efficiency definition, or just remind how can we can measure EQE, the amount of photons out per charge injected into the device. That's what we can measure. But how can we understand this number? We can factor it out into basically 4 factors. The first one is related to charge transport, namely the charge balance factor. I'll have another slide on that. And then we have a percentage of electron-hole pairs in a state that emits light. Here, index singular triplet ratio, kind of in the simple OLED. And then we have radiative, PL quantum yield in a sense. And finally, the light-out coupling process. And this sketch here also tries to summarize where in the OLED are these 4 efficiency factors actually happening. And the product of this is the EQE. Now, already a long time ago, Campbell Scott pointed out how you can think of the charge balance. Well, this is a nice sketch showing, again, if we have hole injection, JH is the hole current. We want to avoid leakage of holes through the cathode. We want to avoid leakage of electrons on the anode side. But what we want recombination in the middle of both of these. We need to have here not only a balance of currents meeting in the middle, but there should also be a high enough cross-section that the electron and hole actually meet and recombine. So here, this gamma is kind of a Langevin recombination prefactor, which in theory you could think if recombination would be suppressed, then the holes would just walk through without recombining, and the electrons would also walk through. So this is we not only need balance, but we also need strong enough recombination to have an efficient device. And now this is the sketch, how we can understand. And this is an example of a simulation of a 4-layer OLED where we draw the electron current. On the right-hand side, there is an electron injection from the cathode. So the blue line is the current of electrons. And you see that the current is consumed here in the central emitting layer, because that's where recombination is happening. And on the left, we have the green line is the whole current, and also that one is consumed in the center, this particle flux, and it is almost zero at the other side. So this is an ideal case. We have charge balance of 1, basically. If there would be finite currents of charges exiting here, then that would be not good. So that's a first example of a simulation output where you can visualize where are the electrons' hole currents flowing in the device. Now, just this overview picture, what kind of material parameters do you have to know in order to do such simulations? Of course, we need the energy diagram of HOMO-LUMO levels. We need to know the layer thicknesses, and then for the material parameters, for each layer, we need to know the electron hole mobility of the carriers, and you can optionally also introduce charge trapping and doping, especially for P or N-doped charge transport layers. And what you get out is IV curve. So these are signals that you can measure, but you also get cross-sections which you cannot easily measure, but which give you more insight. So this cross-section on the bottom right is an example of electron and hole profiles. So the density here, we see some spikes. The spikes basically mean that, for instance, the electron in the blue curve, sorry, these are the holes. We usually plot the anode on the left. So the holes penetrate from the left, and then there is a spike, meaning that they are accumulating at the energetic barrier between two different layers. And so this is typical to see spikes, which is a sign of energy barriers between two layers. So we've seen charge spikes, but also in this example. So ideally, in an ideal 3-layer OLED, you want to have charge confinement in the central layer, and the boundary layers are only transporting, and they also should block the carrier. So the electron would come in here and would be blocked here, and vice versa. The hole would enter here and would be blocked here. And that's what you can kind of see here. The blue curve, and the holes are blocked at this small barrier as well as here, and the electrons as well are coming from the right, are first blocked at this barrier, and then another barrier here prevents the red hole, the red electrons to go to the anode. And now finally, for Langevin recombination, we have more recombination the more carriers we have at the same location. So think about the product of this red and blue curve. The product will give us the recombination zone. So that's where the exciton is formed. Yeah, so it's in very, very narrow region these excitons are formed. And the excitons can then start to diffuse around to transfer their energy to guest excitons or to diode opens and so on. So this is already a kind of interesting simulation here, because we see that maybe in some cases we can have light generation at both sides of the emissive layer and not just uniform across the emissive layer, but really have strong increase of recombination on both sides within the emissive layer.
Could you explain why it's just significantly the interface, but only for like submagnetic and then go through?
So we have to bear in mind that the scale, we're drawing a logarithmic scale of densities. So what we're seeing down here is not so relevant for the device operation. You mean that the charge density here, I mean, here we have orders of magnitude, more carriers, more holes in the EML than penetration of holes into the ETL. So in the ETL we have almost no holes, and in the HTL we almost have no electrons. Is that your question, or why?
Just so much just as the interface.
It has to, well, it's always a question what kind of physical model we input into the software, right? So in the software we assume thermal equilibrium. So the Fermi level is in steady state. We have a constant Fermi level. All right, it's continuous at the interface, and So the barrier, because there's this barrier, it's a Boltzmann factor, e to the minus barrier divided by kt. That gives the ratio of charge on the left and charge on the right of the interface. Yeah. Yeah.
Since you're the building of the population of holes and electrons are in different layers, because you have the growing of the holes, for example, one layer and the other. So when you look at the recombination profile, do you mean the excitons that are formed in the emitting layer, or are these excitons that are like exciplex states?
No, the exciplex state in our terminology, it would be between, or across a layer even, right? But in our software, we don't.
Your holes have not penetrated yet in the massive concentration of holes and electrons are in different layers. The electrons are in the emitting layer and the hole or the vice versa. And the holes are in the transport layer. So when you look at the recombination profile,
No, I mean the holes are in the HDL and the EML, but not in the ETL.
yeah.
And this is opposite
No,
for
I mean,
excellent.
the electrons where so that interface, the electron is the red one, isn't
Yeah.
it? So the concentration, the largest concentration is in the emitting layer.
Then on this boundary.
The holes are in the transport layer.
Okay, yes, it's. You could think that this interface and exciplex is being formed, yeah.
So that recombination
But-
profile there corresponds to the excited states in the emitting layer, or the largest contribution of exciplex states.
But usually, what the photons that are emitted are usually from the EML. And sometimes you see photons that could come from exciplex, but it's maybe less often, yeah.
So the graph on the bottom left.
Yeah.
I think the recombination happens more likely on the side of the light emitting layer than in the right middle of the light emitting layer. Is this like can it improve or just like computational result?
Yes, we have a method that Marcus has actually developed and applied. In his poster, you will see that we can apply an optical fitting method to extract the most likely origin, where did the photons come from. And that method also suggests that indeed it can be a split emission zone. I will get to that later, yes. Okay, now because this year is 30 years of OLED, so this is the very basic Kodak OLED from 30 years ago. It's the first efficient thin film OLED that was, in '87 made. Later on, I also started on OLED research, and this is in my first publication on simulation of OLEDs. I tried to describe the pulsed experiment. So we apply a voltage pulse. After some delay, we have emission, the red curves here. And then after turn-off, we still have some delayed emission from this OLED. And then we have the current measured. We have some reverse current and the off state. And this is what I tried to do at that time, just qualitatively get a similar result. And you see, don't compare the axis, because you will see that currents and so on, it's not quantitatively agreeing, but it was just the first attempt to understand the dynamic processes in the OLEDs. Then later on, we also looked at not bilayer, but multi-layer OLEDs. This is a 4-layer OLED where we have emission from this blue fluorescent material. But surprisingly, both in the measurement and also in the simulation, we found that there is an initial overshoot of light. So we plot here the exciton density across the device at different times after voltage turn on. So at time 0, we turn on the voltage, and after some time until charges have migrated, they need transfer time to cross the layers, and then they generate excitons, and then the exciton decays. So this is a dynamic turn-on behavior that you can do with this kind of simulation. Now, let's go a bit deeper into the model. So these are simulation examples, but now for OLEDs, we need to start with charge transport. That's the green box and recombination. Then the exciton part is diffusion, transfer, and decay. And finally, there's the light-out coupling. And for solar cells, this is just the opposite around. That's why we also do solar cell simulation. But we usually do also sweeping of parameters to understand what's going on, what influence has a material property on the result, on the performance of the cell, and we can do optimization and fitting. Now the equations. First, the drift diffusion equations. We have a Poisson equation that describes for a given distribution of holes, P, and electrons, N, we will have a consistent change of electric field across the layer. And we could also have charge traps that are mentioned here. Then we can express the semiconductor material has a current composed of a drift current, which is proportional to the mobility times density N times electric field. And we have a diffusion part which goes with the gradient of the charge density. So that's general for any semiconductor. And then charge continuity equation, what does it mean? I think I have a cartoon here. So this cartoon tries to explain what does continuity mean. So we consider not the whole OLED, but just 1 nanometer box. And this 1 nanometer box is here, this little house. And we have some type of carrier here. The balloon is entering. And inside the box, we have destruction of carriers. This means recombination. The charge gets recombined and it transforms into an exciton, right? So it disappears from the charge continuity equation. Or, so we can have destruction, but we could also have generation. If an exciton falls apart, you could then again have free carriers. So that would be a generation of carriers. And finally, we have then this continuity equation, which simply means that inside this little box, the rate of change of this quantity, let's say we're looking at carriers, will be this equal to the either generation. So this Q is simply the sum of generation minus recombination. So we either destroy or generate carriers inside the box. And the additional effect is that we can have a rearrangement of carriers according to the gradient of the flux. And in the electron hole flux, this is just the current. So we have gradient of J, which is the second term. If you have more current right than left, then the carriers will rearrange. So the continuity equation is a basic concept which applies to electrons, to holes, but also to excitons. So excitons as well, if they are generated in this box, then they could be destroyed, they could have energy transfer, but they can rearrange. And the rearrangement is only driven by the gradient of the current. And since the exciton is neutral, it can only diffuse. There will be no drift influence to the exciton. The exciton can only diffuse. Okay, that's a remark here. So that kind of explains the green equations. Yes, and then we have the exciton equations. And you see some frames here. There is some coupling because the generation term in the OLEDs, we have whole P times N. That's the Langevin recombination. And so we take away charges, but we then add them into the exciton equation. That's how these equations couple. And later on, we want to have radiation from the exciton. And that's taken care of by the light-out coupling model. That's the blue box. And last but not least, we can also consider electrothermal coupling. So we could have Joule heating. Because of the current flux, the current can give heat. And this rises the temperature. And the temperature then should also be considered in the charge mobility and so on. So that's the latest development. And these equations, we can either solve them in steady state, in transient, and also in frequency domain. And for all of these three, there are experimental techniques. So we have for a certain technique, we also have the right simulation method. And keep in mind that the solution that we get here, we consider the organic semiconductor as a continuum, but nevertheless, we have to we have to sample at certain points. We will draw the density of carriers. So we typically choose a cell width, let's say a nanometer, or the size of a molecule is a typical discretization that we take. And then I walk you through some physics of the model. What are the ingredients? We have charge injection at the electrodes, so between metal and organic. We have an energy barrier. Let's say this is the dashed Gaussian is the LUMO in the semiconductor, and the work function of the metal is down here. So we would have an expected large injection barrier, but because we have an electric field at the contact, we will actually lower this barrier, and this is kind of a Schottky effect. So finally, the actual barrier can be lowered due to this field and due to the image potential, which is also indicated here with this, for Coulomb potential. Moreover, if we consider that we have not just one sharp energy level of the semiconductor, but a Gaussian, we will actually, basically, we will fill a part of the Gaussian density of states, and this will determine the charge density at the contact for our simulation. Then I mentioned charge trapping. This is the equation that we solve. We update the number of filled traps NT according to a capture term having a C as a prefactor. And so the more free carriers we have, the more we will trap. And then we have some escape. Each trapped electron has a chance to escape, but the escape depends on the temperature. So, and the energy difference between free carrier and trapped carrier. This is a typical equation to solve. Then, in terms of Gaussian disorder model, well, there are two approaches to model this. There are also people who solve the transport with Monte Carlo simulation in 3 dimensions, which takes a lot of computation time, but they can sample the energy landscape in 3D. That's a bonus. But we also propose that you could simplify this by assuming a transport level here, which has free carriers, and the exponential tail could kind of mimic the Gaussian tail, and especially in dynamic experiments, this is a quite valid approach as we see when we compare with measurements. So this is one example of charge trapping modeling. If we apply a voltage step at time 0, then we get a current and a transit time effect here. And finally, we have the steady state current. But if we assume certain charge traps, either with a slow or fast means a small capture rate or a large capture rate, we see a difference in the transit time. So the peak position of this refers to the transit time. And this fraction of the two times has to do with the fraction of free carriers divided by the total carriers. This theta number is also known from the literature, and we see it here in the transient experiment. Okay, Langevin recombination, just to remind you, is proportional to the electron hole density, n times p, but also to the charge mobility, mu n and mu p. And then if the question is whether a trapped carrier can also recombine later on, and indeed in the software we can activate this process called Shockley-Reed-Hall, where for instance, there's a dashed line here represents an electron trap state. It can be filled by the free electron is trapped here. And in a second step, there can be holes coming by. The blue dot is the hole that walks by and recombines with the electron here in the trap. And this gives rise to some current flow. And this kind of current flow is actually visible in organic photodiodes. If you look at photodiodes IV curve, with or without the shock read Hall process, you have a much different current level. The blue one is with the shock read Hall recombination, the red one without. And interestingly, this could also be important for dye dopants. If you have dye molecules added into a host, maybe a charge comes by and gets trapped first, and then later on comes the other charge, and then the recombination could be happening. So maybe this kind of process should be considered then as well. Then popular technique to measure OLEDs is impedance spectroscopy. What is impedance spectroscopy? Basically, we apply an offset voltage V0, and we add a modulation with a certain frequency and a certain AC amplitude. We apply this blue voltage. Usually the AC amplitude is only less than 100 millivolts. And then we measure the current, how it is. Also here we have an offset and a phase. We have a complex quantity for the current, and we can get the admittance Y. And the admittance is mathematically divided into a real part, which we call conductance. And there's an imaginary part, which we write as a product of frequency omega times C. So this is just a way to divide things in a real and imaginary part. And the capacitance is usually quite interesting to study. I don't go into detail how we simulate this, so we can solve the equations in frequency domain. And what we get is something more refined than just an equivalent circuit model, because equivalent circuit models are simple, but here we're using a space-dependent model, so drift diffusion equations solved in space. And what we get at small frequency, we start out at a resistance. I mean, the impedance has a zero imaginary part at low frequency, but then the imaginary part gets negative. And instead of a simple single arc, we can have fancy effects like charge trapping. Would be the green curve would be just charge trapping. We have an additional circle, and then the main circle, where the main circle has a dip on the side. You see it's not a perfect circle because there is a transit time effect. The space charge limited current flow, the carriers have a certain mobility and a certain transit time. The inverse of the transit time gives you a frequency that you see here, a little kink. That's the transit time frequency. And then in addition, if you have heating of Joule heating, if the current is allowed to generate heat, at least in the model we can allow or not allow, but in reality you always have at high current density. In the experiment you'll have a temperature rise. If you touch an OLED lighting panel, it can be 40 degrees Celsius and not room temperature. So that means there is heating, Joule heating. And the question is, is it visible in a capacitance measurement? Yes, indeed, it is visible. We have a model here that predicts that there is a so-called negative capacitance effect. So we see a small semicircle into the upper half here of the graph, which is very unexpected, and it has indeed to do with self-heating, as we have shown in these publications that are visible in the bottom. Okay, capacitance, is interesting because you can measure capacitance versus voltage at a certain frequency. For instance, at low frequency, we can measure capacitance versus voltage. And usually, if you apply a reverse bias, so in negative volts, if we have 10 volts negative, the device will simply be empty. There will be just a parallel plate capacitor. So it's the geometrical capacitance value that we see here. The software anyway normalizes it so you can check the meaning. One means, it is the geometrical capacitance. And not only the signal that you could measure is simulated here, but the simulation gives you also the cross-section in the device. So in negative bias, here we look at the carrier density. Dark blue means the device is completely empty. Only the contact, we have some carriers. And then at 0 volt or positive bias, we start to inject carriers. and then the device is crowded with carriers above in forward bias. And when the injection starts, you will have an increase of capacitance. So that's typical behavior of any organic device that you apply a capacitance voltage sweep. You usually have a peak that is indicative of injection of carriers. So that's a simple example how it looks like. Now, what we are also working on is modeling stacked devices. If you have an OLED, a white OLED with a red, green, blue unit, you're stacking different OLEDs on top of each other, and then in the middle of, between the two devices, you should consider, for the OLED actually it's this case here, where you can have charge generation. So the electron from this right unit here, from this OLED, there is an electron in the HOMO that jumps into the LUMO of the neighboring unit. So we can generate carriers at this interface between first and second OLED. And similar process you would also expect, but opposite direction would be for the tandem solar cell. And for the tandem OLED, this is the first simulation result. You see the hole carrier density. On the anode side, we have a lot of holes. And then at the right unit here, again, we have a high carrier density. So that shows that we will also in the future simulate electrically tandem OLEDs. And then I mentioned that we want to simulate signals that look like a measurement, well, if you compare the two. So you need, in the model, you also need to take care of realistic issues like series resistance. Series resistance can happen in the ITO pad. The ITO has a limited conductivity and gives you additional voltage drop. And this is simply saying that the applied voltage from the instrument will not be applied directly at the device because there is an ITO in between. And in addition, sometimes the materials have leakage. So there can be a current not through the semiconductor device, but through some leakage spots. And maybe you even could have some stray capacitance. So we have these additional circuit elements that you can activate in the model for realistic comparison. Let's jump on. Now, finally, the second part of this presentation is about excitons. So we briefly I introduced the exciton physics that is in our model. Let's look at the TADF system, which is as simple as possible. So we have a singlet state up here and a triplet state with a lower energy. And the choice of parameters here was chosen that we can apply analytical solution to the result. So what we assumed here is no radiative. We have no radiative emission from the triplet state, and we also have no non-radiative rate from the singlet state, but we do have KRF, means the radiative rate fluorescence of the singlet. And then we have the intersystem crossing rate KT and the reverse intersystem crossing rate KS. This is the meaning here. And now for this kind of system, we can do some simulation. So what do? We use electron hole transport recombination, and then we apply, for instance, a 5 volts. And then at a certain time we switch to negative volt, and then we will still have excitons that can decay or that can have delayed fluorescence. And these are the parameters we chose for this test. So we have the conversion rate here from singlet to triplet. It's 1 per microsecond here in this example. And in the opposite direction, we have the thermal activation here as an example. And then we have the simulation result are the blue dots from ZFOS, and the model is dashed line. What is this model? It's basically the internal quantum efficiency. We can write it with this formula here, where phi t and phi s have the meaning of phi t is the fraction of singlets that become a triplet, and phi s is the fraction of triplet that becomes a singlet. And adding these numbers into the equation gives us a reference solution that we can benchmark against for our simulation in blue. So this is steady state calculation versus temperature. From low temperature we have poor efficiency, high temperature we have high efficiency as expected from the TADF systems. And of course this behavior depends on the singlet triplet splitting. And now we look at the transient behavior. So at the first we have again a certain voltage applied, and at a certain time here at the dashed line we switch off the voltage, and then these excitons, they can still continue with reverse intersystem crossing, and we can still have the delayed fluorescence. So we have direct and delayed fluorescence. And again we have a full line, which is our simulation result with software ZFOS, and the dashed line is a reference solution, which is an analytical solution. I think it derived in this paper. So we see here the slope or the time constant lambda 1 and lambda 2 are related to all the input parameters of this test case: the radiative rate, the transfer rate KT, reverse, intersystem crossing rates, and the reverse rate of it. All these rates I listed before. So this is a sanity check that indeed the simulation result is in agreement with this analytical solution here. Now this is at one fixed temperature, but if we would change the temperature, you could repeat the simulation for low temperature 70 Kelvin up to 430 Kelvin, and you see that indeed the steady state kind of brightness will go up with temperature, and at the time when you switch off the voltage, then the direct fluorescence goes fast, but then the slow component will be temperature dependent, and the slope here, notice here we have a logarithmic scale, so exponential shape will be a line here, and so this second exponential shape here will have a higher slope here in the log scale because the rate is higher at higher temperature. So this is all looking reasonable. We indeed are able to describe the TADF process as it would be seen in a pulsed experiment, not optically pulsed, but electrically pulsed. So we apply a voltage pulse and measure the light output. So this is an alternative to kind of photophysics, to just directly work with the OLED, apply voltage, and see how the delayed fluorescence comes out. At this stage, this is a simulation result. A slide further, I'll show you a measurement. Again, this is a similar result where we not only show the decay part, but also the rise. At the initial voltage onset, there will be a ramp or a rise of light output, which is also strongly dependent on the temperature. Now this is an example not very realistic, because you wouldn't never expect such a strong change of emission spectrum with temperature. But in the model, of course, you can plug in some numbers and exaggerate a bit. So here we have an exaggerated example where at low temperature we have a certain color coordinate. So at low temperature we have 200 Kelvin is the red curve. We have a long wavelength contribution, and then at high temperature the high energy states emit more, so we have a more bluish emission. So this is just proof of concept. It's not a realistic example, but just shows you that we can simulate everything from charge to photon. The photon has this spectral information, so we get the full spectral output. And now a real device that was measured by Marcus in our ZAW lab. We have a collaboration with Professor J.J. Kim in Seoul National University, where they fabricated co-host TADF OLEDs. And what we did, we measured them with our PIOS measurement instrument. We have an optional cryostat chamber, a small one, where we can add the photodiode or photomultiplier tube in order to record the decay after voltage turnoff. So the upper measurement is the onset, so the on voltage versus temperature between 200 and 300 Kelvin. We see that the overall light output is much higher at high temperature, so more efficient at room temperature, as expected from TADF. And please, and also notice that the time it takes to have certain on light output will also depend on the mobility of the charge carriers, because carriers are more mobile at room temperature rather than at 200 Kelvin, so the dynamics of the onset will also be sensitive to that. And then in the decay part, when we turn off the voltage and we normalize the light output before the turn off, then we see here very interesting things happening. At low temperature, we have a slow component, a slow drop. So the slope here is smaller than at room temperature. At 320 Kelvin, we have a fast decay as expected from TADF process. So this behaves exactly as we had simulated here, well, at least qualitatively. And now you may argue, what is happening with this overshoot? Why should we have more light after we turn off than in the DC state here? This is a surprising effect, but it can actually be explained by something that was already described many years ago by Sebastian Reinecke, where he has looked at the phosphorescent OLED. The emission layer is doped with phosphor, and then in the steady state you have, or at least he was describing that probably we have excess carriers on the right and on the left of the emission layer, and as we turn off the voltage, this is actually his measurement, you see that there is this overshoot that can be even higher than the steady state value, because the electron and hole are still in the emission layer, and instead of being pushed to the boundary, they will go back to the electrodes and have another chance to recombine. So there will be additional recombination happening that gives rise to this overshoot here. And our simulation actually nicely reproduces this effect. You can see this overshoot is a very distinct position, and this is actually a more general effect, nothing directly related to TADF. It just shows up here in TADF as well, but it's known from phosphorescent OLEDs. And in order to further visualize this, this is an example of a phosphorescent OLED which has an ERPI-doped emission layer, and you see from the energy barrier that we have in a homolumo diagram here, the holes will have a barrier here, so they cannot escape. And the electrons have a barrier here also. So this gives a pileup of carriers. So recombination would be on both sides of that layer. And now the energy diagram in the 5-volt forward bias, you see that the electrons that come from the cathode, they want to go downwards. They want to slide down the energy diagram. And there are a few steps. And here at the big step, they will pile up. So the green curve is the quasi-Fermi energy profile, which is just another representation of charge carrier density. You can translate quasi-Fermi energy into carrier density. So the little bump here is the indication of electron accumulation. And the holes have, in the purple line here, we also have a bump because the holes are piling up at this barrier here. This is the on state. Now if you turn off the OLED, we have a different band diagram, because now we have applied 0 volt. As you can see, the quasi-Fermi energy on the left is the same as on the right. What we see here is just the built-in potential after you turn off the OLED. So now instead of the electrons walking from right to left, now the electrons want to go from left to right, because we have turned off the OLED. So the electrons go back to the cathode, and the holes go back to the anode. And during this process, we see here, as a function of time, first the electrons are piling up here, and this is the Y scale is the time progression. As a function of time, they will go back to the cathode, enter this layer. The opposite happens for the holes. So the product of electron hole will be the recombination. Recombination profile versus time is shown here. So the reason for this red, this strong recombination is the electron and hole recombination, And finally, we see the emission versus wavelength. So we have here wavelength versus time. So this is a time-resolved EL decay that we can calculate. And the integral of this spectrum gives us the signal that you actually can measure. So we go back. This was measured for the phosphorescent OLED, the spike. Same here for the TADF OLED. And the details are hidden here in these profiles. As a function of time, we have recombination happening and giving this bump after turn-off. Okay, so that already shows that the excitons are maybe not there where you expect them. So they can pile up at the boundaries. And the question is it possible to measure where they really are? And not just simulate this, but actually measure. So in general, you don't know in advance if the excitons or the emission zone is on the left or on the right, or whether it's more in the center of the emission layer, or maybe more uniformly distributed, or even a split case as we have shown here. So the way, the method that we propose to use is angular emission measurements, shown here, angle versus the spectrum versus angle, and then use an emission zone fitting algorithm that we have implemented in ZFUS and published some years ago, some examples. And this algorithm allows you to estimate where inside the OLED stack, where the excitons have emitted the photons. And in addition, you can also estimate the luminescence spectrum of the emissive molecules. This seems to be a powerful algorithm. And yes, Marcus will show it in his poster this week, that he applied this methodology to a ERP-doped CBP emission layer. And he found that at different current density, the emission zone is changing the ratio, so that you could have more exciton on the right-hand side for low current, but at high current, the higher exciton density will be on the left side. So the balance changes with the current density flowing through. And this is directly visible because we analyzed spectra versus viewing angle. And the details he will explain at the poster. One thing to note is that from this analysis, we find that the charge factor, so I should show here the full data. We have here measured efficiency in the triangle symbols here. So at a certain voltage, we have a maximum efficiency. And then the reason why we have so efficiency roll-off here, the reason is actually the red curve. It analyzed the charge balance factor, and it goes down with increasing voltage, and that's the reason why we have efficiency roll-off. So there is no additional assumption to be made, no TPQ or TTA, simply just charge balance, changing charge balance can give rise to efficiency roll-off. Okay. For completeness, nevertheless, let me mention the TTA and TPQ process, which is still relevant. So the way we model this, of course, the excitons, a mono-exponential decay is what you would expect if you only have one rate constant for decay, for emission or non-radiative decay. But now if we assume a TTA, this is a bimolecular process, so we have a square here of the N and the prefactor KTTA. So this kind of decay has a different transient behavior as the TPQ, which is triple polaron quenching, where we have the product of polaron density P and N. And while TPQ would be mono-exponential, TTA is not. And in the case of TTA, you would nevertheless also have a possibility of delayed fluorescence due to singlets that are generated from TTA. This was shown by the Britting group that indeed you can have delayed fluorescence. And if we directly compare mono-exponential or not, indeed in this simulation example, just some proof of principle simulation, you see that the TPQ process leads to a mono-exponential red line here, while for TTA process we have a decay which is not mono-exponential. Okay, now TPQ, let's have a look at this. This is another example. Indeed, it can be used to describe efficiency roll-off. You see that the calculation of the current efficiency or charge balance here, yeah, we plot the current efficiency. Without TPQ, we have a constant. With TPQ, we can generate a decrease or a roll-off. And one nice study that was done by a group in Japan was to quantify the TPQ rate by looking at hole-only devices as well as electron-only device. So for hole-only devices, they ran through a current and they looked at the PL intensity, and they found that most likely the TPQ process is more happening on the left of the layer, where we have a lot of charge carrier density. And this is shown here by the simulation of the profile of carriers. And with this comparison, they fitted the simulation to JV curves and extracted this TPQ coefficient. Yes. And an additional thing to consider, sometimes if you have a host-guest system and you drive at high currents, sometimes you can observe that not only you have emission from the guest, but at high current density, maybe there is increasing amount of emission from the host. And this graph here is actually a logarithmic intensity of EL spectra. So it's a small effect, but nevertheless, so the way we describe it here, we kind of assume that there is saturation. If the guests are already all occupied, then we can no longer transfer from host to guest. And this gives rise to this increase of luminescence in the blue, in the high energy part of the spectrum. Okay, to summarize what kind of exciton physics we can activate in the model. This is from the software manual. Well, it's basically everything that I mentioned in the talk. We have generation of excitons through the Langevin process. Then we have a possible redistribution of excitons across the layer. So bear in mind, if we have calculated a very sharp recombination profile, this could still mean that after diffusion of excitons, it will smear out a bit. So this is due to this term here. And then we have radiative emission, non-radiative emission, optional annihilation by the TTA process. Then we could have Förster energy transfer or Dexter energy transfer that is described by this line here. Then we have TADF with the typical exponential Boltzmann factor. And TTA again here, yeah. And then TPQ on the bottom line. So we have different kinds of TPQ. You could, whatever you assume, I mean, you could assume that the trapped carriers are quenching the excitons, or only the mobile carriers, or it could be the electrons or holes. That's why we have 4 different possible TPQ terms. So in principle, it's customizable. Whatever you believe, you can activate each individual term here in the model. And finally, yeah, if you believe that the excitons are generated due to light absorption, so in the solar cell, for instance, then you have this term here at the end. Okay, that's the summary of the model. And with this, I think I'm at the end of this presentation. Yeah, the summary is the electronic processes are well modeled with the drift diffusion model, and we can solve it in steady state, AC, and in transient state. And if you have time, I can make a quick demo of the software. The exciton dynamics are, we can resolve it in space and time and in spectrum, emission spectrum. And so that gives a lot more information than just assuming a an exciton density with 0 dimension in space. So we have really the spatial resolution, and I have given you some examples of TADF, both in experiments as well as model. Okay, I'll make maybe a brief demo.